Okay, so now we are going to be exploring electric fields for more realistic distributions of charge. So let's sort of summarize what we've done so far. We've been considering electric fields produced by charged particles that are sort of point particles. So there's a charged particle here of charge Q1, there's a charged particle here, charge Q2, there could be a charged particle over here, right? I could have charge Q3, and the electric field at some point, say right here, is just the sum of the electric field. So we imagine that we got this from doing experiments. So at this point, the electric field is the electric field due to the particle of charge Q1, which we'll call E1, the electric field due to the particle of charge Q2, which we call E2, plus the electric field of the particle of charge Q3, which we call E3. So we basically conclude that the electric field is the sum over the electric field produced by each particle. So EI is the electric field produced by particle I, and we have to sum from I equals 1 to I equals n, some number. Okay, but the real world is not as simple as this, in the sense that instead of having particles, little tiny point particles that produce electric fields, we really should be thinking of a region of space where charge is sort of uniformly spread out. So if it's a two-dimensional region, then there's a region there where charge is spread out over that region, and things get a little bit tricky in the sense that we have to hone in on a tiny little region. So this could be a tiny little region dx dy if we want in x and y coordinates, and it has a certain amount of charge dq, and so the principle is unchanged. It's this mathematical result, which tells us that we have to add all of the electric fields, but the charge is now continuously distributed. So that expression changes. So each little tiny bit of space produces an electric field, a tiny little electric field, which is equal to K times the tiny amount of charge that's there. So instead of Q, we have dQ, an infinitesimally small amount of charge. We divide by the distance squared to wherever we want the field. Let's say we want the field here. Then there's an R there. And then we have a unit vector, r hat. So the principle is the same. We just have an infinitesimally small electric field produced by the infinitesimally small amount of charge at that location. So we have to sort of divide the space up into tiny little pieces of charge and add them all up. So the net electric field now is going to look like not a sum, but an integral. So it's an integral over this kind of object. And this can be a very complicated thing. So worst case scenario, we have to take a brute force approach, which means we just have to integrate over all of the charge to get the electric field at some location. So let's think about an example. Let's imagine that we place, let's make a simple configuration of continuous charge. Say something like charge distributed over a line. So maybe this could be the x-axis, and let's make it a little bit thick just for illustrative purposes. So there's charge over a one-dimensional region, sort of uniformly spread out. So we could imagine making little plus signs indicating the charge. And we'll space them out a little bit so that it doesn't take us forever, but it also captures the fact that the charge is uniformly distributed over a one-dimensional region like that. And let's say that we have a charge density. Okay, so the charge density, right, it's the amount of charge divided by the length. Let's say we know that, and it's given as lambda. And the question is, let's find the electric field. So we have to find the electric field in space. So we could imagine that, given the way the charge is distributed, that this is the y direction and this is the x direction. And we can think of this in terms of the xy plane. And when we do that, let's say we want the electric field at some random location there. Okay, so we have the distance to that point. There's some angle here that comes into play that might be useful to us. And our electric field is some object that has both magnitude and direction at this location. And we want a general expression. So our electric field is going to be an integral over this entire infinitely long one-dimensional region, the x-axis. And we have to figure out how to write the infinitesimally small electric field produced by a tiny little region like this. Right? So this is a tiny little region along the x-axis, which we would call dx. Right? In the region dx, there's an amount of charge, dq, an infinitesimally small amount of charge, and that produces an electric field, dE, an infinitesimally small electric field, at some point, and we have to integrate that to get the net electric field. And we can think of this, given how we've distributed the charge, as an electric field in the x direction. So this could be, let me make, given that I chose this little dx, it's really the distance. Let's consider first the distance to this point. Okay, so that's our r. And so our angle is really this. That's our angle theta. And that angle is changing as we think of contributions from other little dx's. Now, these are all the dx's. And the distance from here to there comes into play. This distance here, the distance from here to there. So clearly the angle and the distance are changing. And so we are really integrating something that has an x component, right? Little piece produces a little x component to the electric field and a little y component to the electric field. So I'm going off the page there. I'll lower this a little bit. DEY. And so we are really integrating this kind of a quantity where we can separate out the x and the y part. And let's do these separately. So the x component of the field looks like what? So we have k is the constant. We have the charge density that goes into figuring out how much charge there is, right? How much charge is there in a little region dx? Well, that's dq is equal to the density times the length. But that's an infinitesimally small length. So that's how much charge we have. We have to write everything in this integral in terms of x because we're integrating in x. We have to write things down in terms of how they depend on x. So we have k lambda dx for dq. We have to write the r squared. We have to divide by r squared. And we have to take the x part of this. So, right, our right triangle, if this is the dq that we care about, then our right triangle looks like this, where this is the y part and this is the x part and this is theta. So we need to find, let's just leave this as r squared for the time being. We'll write it in terms of x and y in a minute. But we care about the x part of this, which involves the cosine of theta. And the y part of this will involve the sine of theta. So this is actually d ex. Okay, so that's the actual x component, the infinitesimally small x component. And by looking at the geometry, right, we know that the cosine of theta, now we're going to try to write this in terms of x and y, is the adjacent over the hypotenuse, and the adjacent side is the x value over the hypotenuse, which is x squared plus y squared square root. So we can write cosine of theta in terms of x, and of course the distance in terms of x is simply x squared plus y squared square root. And so we can put this all into one integral and get that the x component of the electric field is k times lambda. These are constants, so we can pull them out of the integral, and we're going to integrate from, since we're integrating in the x, we have to go from x equals minus infinity, right, all the way over there, to all the way over there. Each little piece contributes, and we're integrating from the pieces that exist all the way over there at minus infinity in the x direction, all the way to plus infinity to the right. So we go to infinity on the right, and let's replace the r squared with this quantity squared and the cosine of theta with this. And so we have a full expression in terms of x. In fact, it's in terms of x and y. And unsurprisingly, we get the 3/2 value in the x. Okay, so that's the x component of this. And let's write down the y component of this, and then we'll actually do the integrals. So the y component of this involves k times lambda. We're going to integrate in the x times the sine of theta. And the sine of theta is just, let's write it here, the sine of theta is y, right? It's the opposite over the hypotenuse, so it's